Okay, boys, I hope you're doing well. Hope you're healthy and safe. And I miss you. And I'm looking forward to working together over the next 2 months, even if it's from afar. So we're going to get right into things. And the first thing we're going to start to do for 2 weeks is this general idea of undoing a rate by integrating it. And we've looked a little bit at this um, and what that gets us. And we're going to take a deeper dive with three general looks for the next couple of weeks. The first being the usual position, velocity, and acceleration. Right. The other look is kind of integrating any other rate to get the net effect of that rate. And the third is a differential equation, which we can also think of as a rate, and we're going to undo that to solve. So let's get right into position, velocity, acceleration. We've, of course, done this before, and when we take the instantaneous rate of change of position, i.e. derivative, we get the velocity, and when we differentiate the velocity, we get the acceleration. So to work down that chain, we differentiate. Of course, we can also work up that chain by integrating, right, which undoes differentiating. So for this particular example, we're going to get right into a problem. So let's look at a problem where we have velocity, and they're given a couple questions pertaining to the velocity of that particle. So I'll give you a minute to read it. Okay, less than a minute. Note we're given velocity of this particle. It's moving along a line for 5 seconds. And we're also given the initial position. So it starts at 10. Right? So wherever it is in any moment is 10, where it begins on a line, plus or minus the net distance it moved over that particular interval. All right, so for part A, it says find all values t for which the speed of the particle is 2. We're not going to focus on that right now, but if we kind of think about that in general broad stroke terms, I would say, okay, speed is kind of like velocity, but different. Velocity, like vectors, has a magnitude, a number, the rate, and also a direction. It can be positive or negative. So speed, however, just is always positive. So the relationship between speed and velocity is that speed is the absolute value of the velocity, right? And so for part A, I just want to know when the absolute value of that velocity function equals 2. And you know what? That's definitely a calculator problem, right? So I would graph that function, and I'd see how many times it intersected the line y equals 2. Okay? So I don't want to spend too much time on that one, but that's a general concept for part A. Okay, part B is really what I want to focus on now. Okay? So for part B, it asks us, okay, we have the velocity. Now write an integral containing expression that gives us a position at any moment t. Okay? And then we're going to use that expression to find the position at 5 seconds. So there are a couple things to remember. Remember that A, this particle starts at 10 units to the right of 0, the origin along a line. All right, so I have to take that into consideration. So whenever it starts, well, wherever it is at any moment t, it's going to bounce off of 10. Now, what I have to do to that starting point, the initial position, is I have to add or subtract the distance traveled over that time period from 0 to t. Now, really what I want to do is I want to work from velocity, which I know, back to the position. Right? So I want to get from the velocity function, which I have, the position at t. So to do so, I'm going to integrate from 0 to t the velocity function. Okay, which in theory gives me the net distance. There's no unit given here, so it's just the net units traveled over the first t seconds. Now, one thing to keep in mind is that this function is a function of t. Okay, the function that I'm setting up, which represents the position at any moment. Now, because that upper bound of my definite integral, lower bound being 0, upper bound being t, so my upper bound is t, I have to have a different variable within my integrand. So we talked a little bit about this when we were looking at this fundamental thing of calculus, if you recall. All right, so really what I want to do is I want to say, okay, I have to change the variable to something not t in my velocity, and then integrate the differential x with respect to that variable, dx. So more specifically, the position at any moment in time t is where it starts, 10, plus or minus. Remember, a definite integral can be minus, which would mean it's moving to the left more than it's moving to the right. The distance it travels from 0 to t, the definite integral of the velocity, and I'm going to change the variable to something not t. 3x to the 6/5 minus x cubed, and then my integrand is in terms of x, therefore I'm integrating with respect to x. Okay. So that's the first part of that. I start with 10, and I add or subtract the distance, the net distance traveled, for which I integrate the velocity over the first t seconds from 0 to t. Okay, once again, recall that this is a function of t. Therefore, my variable within the integrand has to be something other than t. It can be whatever you want, just not t. Okay? So now it says, okay, use that to find the position of the particle at 5 seconds. So we did the hard part. We did the heavy lifting. So now I just have to substitute in a 5 for t. So that means the position at 5 seconds is where it starts, plus the distance it moves over the first 5 seconds, plus x squared, plus, I'm not plugging in a 5 for x yet in the integrand. And now you're saying, well, wow, like that's going to be a nightmare to integrate, and you're right. It's actually not too bad, but I'm going to use my calculator to get that particular value. So I'm going to scroll down a little bit to keep it in the frame. Oops. And then that now becomes a calculator problem. Okay. So I'm going to call upon, hopefully you guys have saw the link on our website where you can download the free version of this. But this is a pretty easy now calculator problem. So I'm going to have to evaluate 10 plus the definite integral, which is math. Function integrate, it's number 9. And it automatically pops up that definite integral template. So lower bound 0 to 5 of the first 5 seconds. That is -2 plus x squared plus 3. Oops, I missed a parenthesis somewhere. What's to the 6/5? Pardon my hastiness. Yeah, that's -2 is not in the power. That should go away. So let me do this correctly. Pull that back up. There we go. Get rid of this parentheses. Yeah, get rid of it all. So I'm going to integrate -2, which is easy enough to integrate. Plus now the quantity x squared plus 3 all to the 6/5 divided by 5, and then minus x cubed. Oops. Right, so again, just recall that that integrand is the velocity from 0 to 5. That represents the net distance traveled of that particle over the first 5 seconds, and plus 10 because I start at 10. Right, so that is the solution. -59 point. And we're going to round to the third decimal, so 0.495. So what happens is this particle, here's 0, starts way over here at 10. And over the first 5 seconds, it's doing a lot of crazy things. But 1, 2, 3, 4, 5. It ends up way over here after 5 seconds at -59.495. Okay. So that's the part of this problem I wanted to review with you now. the idea that to integrate the velocity, you get the net distance traveled, or I guess in this case, we get the first 5-second net distance traveled. We put a 5 in there. Okay, so I hope you enjoyed this video. Pause it, rewind it, take some good notes, call or text or email or Zoom if you have questions. Looking forward to seeing you in live class soon. Take care now.